Good morning. Today we are with Julio Paneque. He is intelligent systems, robotic, and manned aerial vehicles expert, and he's going to talk about ecosystem monitoring. Good morning. How are you?
Good morning. Oh, glad to be here with you today. I'm very good.
Thank you very much for coming today. Can you explain to us how does the ecosystem monitoring work?
Okay, so the concept of ecosystem monitoring is, I think it's very clear, is to gather the most amount of data as possible that we can gather from an ecosystem so we can make the right questions about it. We want to make questions about how is the ecosystem working, how are the species living in it, and most importantly, how are our actions influencing on the ecosystem, and how can we, for example, in the future, wrongly or goodly influence in general in the well-living of all the species in it.
And what are the relevant data for monitoring?
Okay, so the relevant data typically is divided in two sides. For once, we have remote sensing, which is a technique basically having a camera or another sensor installed on a satellite, a drone, or whichever platform we can have. From remote sensing, we gather data such as images, color images, thermal images, multispectral images, a lot of images from, for example, satellites. We can have maybe each couple of days, like every 5 days, we can have images with some more or less small resolution, but with a lot of data about how it's doing, how a patch of ground is doing in different spectrums. Also, we can have, for example, from drones, we also have this kind of cameras, and we can also have more sensors such as LiDARs. When doing flights with the drones, we gather a lot of data about different patches of the ground, but with much more resolution than the satellites. And then we also have another type of sensors, which would also be remote sensing, but they are installed on the ground, which are LiDARs for aerosols. So these LiDARs basically are pointing towards the sky, and they gather the reflectance of different aerosols that we have in the sky, and they are very, very useful for climate monitoring in general, and that's for ecosystem monitoring. Then we have the other kind of sensor, or the other kind of monitoring data, which is in situ sensors. We can install a sensor in a specific place, and then we can use that sensor to monitor, for example, the temperature, the quality of the soil, the wind, or a lot of different variables. There are many, many different variables that we can monitor with these kind of sensors, but we need to go to whichever place we want to install the sensor and install it. This can sometimes be much more difficult than remote sensing because we need to go to the place, but we can also monitor a lot of different variables. And then we also have another kind of monitoring data, which I think is very relevant also, which is the citizen science contributions. So, for example, we rely on citizens to go to a specific place and take an image of whatever they are seeing. For example, it can be a beach, and they can take an image of how is the beach today, and maybe with a lot of images during different days, we can gather information about how is the beach in every season of the year, depending on, for example, the amount of people in it. And yeah, I mean, and there are also many, many different things that we can monitor with data science. No?
And was the citizenship collaborating a lot in the project?
Yeah, I think we have, for example, a very good example of citizen science in this project was the beach monitoring in the Sunghal project and Indalo. We had a system with a metallic platform where the citizens could be, when they arrive to a beach, some specific beaches that we have covered, they would see this metal frame to put their phone in it. So the metal frame said, hey, take a picture here, and with a QR code, send it to us so you can help us monitor how is the beach doing during the year. So I think that's a very good example of citizen science. Yes. Also, there are citizens, for example, taking pictures of horses that we can use to check how is the animal doing and how is the pack moving along for example, a spatial area of conservation, a natural park. Yeah, and I think there are many more examples that we could cover.
Yes, and it's something curious for them, so I think that's the reason why they collaborate in that way. Yeah.
Yeah, yeah. I think citizens are very, very keen to typically. You can see families with children that the children are always very keen to collaborating with this kind of initiative because it's something new for them. It's like, oh, I'm collaborating with scientists.
Everything is a question for them.
For excursions for the middle schools. And also I think that the people that are involved with some of these ecosystems, so for example, people that love horses, people that live in the beach and they want their beaches conserved very well, exactly. Exactly. So these kind of people always contribute a lot. No? So maybe it's not for the citizen, but it's more for the person that is enthusiastic about some topic. No?
Yes. Yeah. And what are the main challenges that scientists have to face in order to obtain the data?
Okay, I think the main challenge is the resolution of the data. So we have two types of resolution: the temporal resolution and the spatial resolution. The temporal resolution is basically in what frequency do I take the data. So, for example, with satellites, we have a very high temporal resolution because every couple of days I can take a picture of a specific place. Okay, and that's very, very useful. And with sensors also, we have a very high temporal resolution because we are taking temperature measurements, for example, every hour. Or every minute, depending on the sensor that we want to explore. But with that, that is a very important thing to have in general because we need to monitor how the ecosystem works. But there is also the spatial resolution. The spatial resolution is how accurate or how close is the data that I'm taking to other similar data that I need to take. For example, if I take an image from a satellite, even if it has a very high temporal resolution, you don't really have the images. Every pixel of the satellite maybe can be of 5 meters times 5 meters, which is a lot because maybe you can have even 2 trees in that area. So it may be good for some things as exploring how good is the soil in that area. But for other things, you don't have enough information to answer some of the questions, no? Because you lack a bit of the resolution. And also you can try to explore these problems with other things such as performing drone flight campaigns, okay, where you can fly and take a lot of images. And in these campaigns, you have very good spatial resolution. And if you do it every day, you can have very good temporal resolution, but that's very costly. And also, if you are doing that, maybe you can be disturbing the ecosystem by monitoring it, because the drones, for example, the in general quadrotors, they are not suitable for being very close to an ecosystem because they can be harmful for horses, for birds, exactly, for all the species, and even for plants. But maybe that's for something that we still have to explore.
For a branch, it cuts it, or
maybe, yeah, maybe that's bad for the drone, and also for the branch.
Yeah. And when scientists have this data, how can they obtain a conclusion? Okay,
so typically when scientists gather all of the data that they want to gather, they start, they cannot publish, this is all the temperature in the last 10 years. That's something that we cannot work with that, no? Because it's a lot of data. They need to generate some intermediate representations. So for example, with LiDAR data, you have a lot of points distributed that are resembling the surface of different elements, trees, ground, buildings, whatever, that you have been flying over. But then you need to transform all of this data, which doesn't have any value by itself. You need to transform it to some other thing. For example, we have some projects where this data is transformed into height of the trees, amount of vegetation, density of the vegetation, and these intermediate representations allow us to respond or even to make some questions about, okay, why is the tree density better here than here? Can we mix this with other sensor information from other projects, maybe with the temperature around the years, to see if there is any correlation, if this is influenced by some human action, pollution in some city, pollution in some other way, some natural disaster. So can we mix this intermediate representation with other data to try to find better answers for our problems or for the future, just to see how the ecosystem works?
Yeah, and what's the LifeWatch ERIC role in this monitoring?
Okay, so actually, I think the example that we just covered is very clear for this, because for processing all of this data, you need to have a lot of computational power, because, for example, if you just process the data for a couple of kilometers, then there is no problem. You can, as a scientist, you can do it with your laptop, and maybe you can cover even one city, one province, or whatever. But if you want to process this data for a whole country, or even for the whole Europe, you need to have a really good infrastructure that covers you in this case. And that's where LifeWatch enters. We cover everything from the registration of the data and the publishing in our infrastructure, to the processing of the data, to the distribution of the data. So we want to help researchers put their data in some place, process their data, and get this intermediate representation, get these correlations with other data, everything very simply, because they already have all the data available. And then, once they have processed the data, we want to help them to distribute the data. We want to help them make the data findable for other researchers, the data and the results, findable for other researchers that may want to ask the same questions as them. And so maybe they can compare between each other, see what methods they are taking into account, and if some results can be mixed with other results to get an even better answers to some of our questions, and so on. No? So that's the role, to make the data available, make the data processable, and make the final results distributable.
And could you mention any example of this?
Okay, so I think a very good example was the last one, with all of the LiDAR processing and so on. And we also have, for example, another use case that we had in one of these ERDF projects, which was for satellite image processing. So we had images from satellites or from high altitude vehicles of a series of terrains in Sierra Nevada. And we had an artificial intelligence model to get the bushes in each of the images, and to count the bushes and to see the amount of bushes along a set of times in the last years. So that's a very interesting use case, because we could support the processing of all of this data with artificial intelligence. We could support the counting of all of these bushes and the generation of results of, okay, how dense is this zone? Has it changed over time? Does this have any implication in the ecosystem? And so on. No? So I think that's a very good example. Yeah.
Yeah, for sure. And talking about acquisition of data, is there another value that LifeWatch ERIC can deliver?
Yeah, I think there is two very clear values that we added during this ERDF projects. And one was the inclusion of a satellite. Okay, we recently launched a satellite, Platero, which is part of a collaborative constellation that now LifeWatch is also part of. We can have images from dozens of different satellites, that we can request images of specific places of the world, and these images have even better resolution than the ones that are available with public satellite imagery. So then a scientist can ask us to deliver these images for them. Maybe they want to have images with a better resolution from Sierra Nevada or from another natural park, and we can help them to achieve this by letting them ask the constellation for these images. So since we have one satellite in the constellation, we have access to all of the satellites with no cost. And I think that's a very important added value. And also we have developed a data logger, okay, which helps the scientist that is gathering data with in situ sensors, because typically these sensors are very hard to configure. And if you want to I have a humidity sensor, and I want to configure it so I upload the data to the cloud. All of this involves a series of steps that they are very complicated to do by a non-experimental scientist, okay, or a non-technical person. So we have really improved this process by simply providing a data logger that can be connected to the sensor. You can say, hey, this is a temperature sensor of this type. And then the data logger takes everything into account from the acquisition of the data to the publishing of the data in the cloud, already federated with us and already saying this is this type of sensor which is installed in this area, and so on, with all the important metadata together. So I think these two are very important contributions that we have made. Yeah.
And you have mentioned that sometimes it can be difficult to access to some type of data, but regarding to the system, is it easy, or can anyone, like a citizen or a researcher that is not that technological, or let's say, is it easy to find the information?
Yeah, I think not only to find information, but it's also very, we are trying to make it easy for the researchers that are non-technological to also provide this kind of workflows, this kind of processing of the data, and do it in a simple way. We are focusing on the non-technical person, but mostly the scientist person, but non-technical. We're focusing on allowing them to provide these kind of results without having an important knowledge of technology. Why? Because through the MyLifeWatch platform, we are providing an ecosystem for a virtual research environment for, hey, simply accessing or easily accessing the data that is already available in the LifeWatch infrastructure, which is already tagged and saying, okay, I want to find humidity data in this area in the last years. If it is there, we are already tagging it and you can find it, okay? We are making this data findable for the researcher. Then, if I want to maybe use this humidity and temperature information to provide some intermediate result to get some conclusion, maybe there is another scientist that has already done it. So you can take the workflow that this scientist has published and use it with your own data. And you can easily cite their work because when you are doing all of this in our infrastructure, everything gets recorded and you can always check what are the researchers that have contributed to your final result.
It's more profitable for everyone.
For everyone, exactly. And most importantly, more easy. And then if you are a researcher that provides this kind of workflows, that does this kind of computation, we make it easier to just provide the code and we can manage how to distribute the computation over our infrastructure without no added effort. No? Okay, so that's, I think, many researchers, they are maybe not super technological persons, but they know a lot of Python or R code, and they are very used to do it. So then they can put that code in a workflow, and we can help them to distribute the workflow, use it in our infrastructure, and they don't need to know a lot about the servers and so on. Yeah.
I see. And talking about the data, again, let's say we have a lot of information, a lot of data that maybe we can think, is it truthful, or how can we depend on that?
Okay, that's, I think it's also a very relevant question, because many times when a researcher or when a research group publishes something, they say, okay, we have collected this data over the last 10 years, and now we have made this processing, and we see that this is the result. Typically, you have to trust this. And we normally rely on other research groups that if they want, they can access this data, try to imitate the programs, and then see if they get the same result. Maybe after some years, we can check if this is true or not. But in LifeWatch, we want to provide an added value in this process. When you are using our infrastructure, the data that you are submitting, the process that you are doing with the data, okay, the process in the workflow that you are using to process the data, and the final result, they are all tracked in a blockchain system that delivers or that verifies that this data with this work provides this result. And you can access this data in this way, you can see this work in this way, and you can see the result here. We are making all of the steps accessible to the public, And we are also, with the blockchain, certifying that step A with step B with step C generates the result D. And I think that's a very important added value, because saying that something is truthful is very different from just, trust me, this works.
Yeah, for sure.
Yeah, it's very important for policymakers also, not only for researchers, but for policymakers that want to make monetary decisions about these results. Yeah. They need to check, and they need something that tells them, yeah, this is true. Don't trust the researcher, trust the system, because this is already tested. Yeah.
And how do you see the future of ecosystem monitoring, and there will be new ways of doing this method of gathering and then processing the data?
I think we have a very bright future for this. As a roboticist that I am, I see that there is a very clear problem that if we want to gather high data with high temporal resolution, okay, so we want to gather maybe at some specific time of the year, we need to check where are all of the nests of different birds, whatever. If we need to gather this kind of data, if we are relying only on drones, okay, with all of these rotor blades making a lot of noise, we are going to disturb the ecosystem. And this is something that it's already in some debate between researchers. So I think that the introduction of new ways of monitoring the system that don't need us to maybe go there with a Land Rover to install 3 sensors, or we don't need to send a quadrotor to just check for the birds. Maybe the birds are fleeing because they don't trust us. Okay, we are introducing, for example, we can introduce new kinds of robot systems. So, for example, a robotic dog system. We can introduce it in the nature with a self-recharging mechanism, so they can be there left forever, taking measurements of whatever we need them to take measurements. So, for example, try to find some nests of these birds, get the humidity of this area, and so on. Just ask the questions and say what we need, and then let the robot do everything. And why can do that? Because we can take the information from already available from LiveWatch, information from satellite images, from drone flights or previous drone flights, and convert all of this information into a proper structure of the scenario that help us guide the robot and say, hey, avoid this area which has a lot of trees and a lot of vegetation, go over here, avoid this area because there are some packs of animals and so on, and we can introduce robots in the wild without disturbing the nature. So I think that's a very interesting new line of research that eventually we may focus on, taking into account the amount of data that we already have that can allow this to happen. Yeah.
Yes. Thank you, Julio, for coming today, because everything was very clear, and thanks.
Okay, thank you for having me today, and I think it was a very, very interesting conversation.
Yeah, for sure. Thank you.
See you.